Welcome back to Calculus 3. I'm Dr. Jeff Groh. Today, we're going to talk about motion. Mostly simple ballistic motion, but if we let r of t equals a position vector, as you know, that will describe some path. As time goes on, the curve passes through different points on the curve. The instantaneous rate of change of position with respect to time is, by definition, the velocity vector. This is the Leibnizian notation for the derivative with respect to time. The Newtonian notation would involve a little dot over the top of the variable. The position vector is a vector emanating from the origin and terminating at a point on the curve. The velocity vector is tangent to the curve, and the magnitude is equal to the speed. Speed, which is the rate of change of arc length along the curve with respect to time, is the norm of the velocity vector. The acceleration vector is the instantaneous rate of change of the velocity vector with respect to time, and that's the second order derivative of the position vector with respect to time. So that's either v dot or r dot dot in the Newtonian notation. Let's look at a simple example. Let's suppose we have r cosine omega t, r sine omega t. Here, r is the radius of a circle. This path is clearly circular. Omega is the angular velocity. If omega has units of radians per second, when we multiply t, the time, in seconds, we end up with radians. So omega is the angular velocity. This is the lowercase omega. The uppercase omega looks like this. The velocity then is, using the chain rule, minus omega r sine omega t. For the first coordinate, derivative of cosine is minus sine, but you have to multiply by the derivative of the inside with respect to t, and that will give you a factor of omega, times the cosine of omega t. Now, what is the dot product of v and r? We know that the curve is a circle of radius r. The vector, position vector r, is a vector emanating from the origin and terminating on the circle. If you calculate the dot product, you'll get a minus r squared omega sine cosine, and then a plus r squared omega sine cosine. So the dot product is 0. That implies then the velocity vector is orthogonal to the position vector. They are at a right angle to each other, which should make a lot of sense given your understanding of the geometry of the circle. Now, the acceleration vector is v dot or r dot dot. Calculating the derivative, we'll get one more factor of omega because of the chain rule. So we'll have minus omega squared r cosine omega t, and then minus omega squared r sine omega t. If you factor out the negative omega squared, you end up with what's left over being exactly the position vector. In other words, the acceleration is in the opposite direction of the position vector. What is more, as the angular velocity increases, the acceleration also increases in magnitude. You can think of this like as follows. If you swing a big heavy object on a rope, around and around and around, the faster you turn, the harder you have to pull back on that rope, the greater that acceleration is. What direction are you pulling on the rope? You're pulling directly back. When I was young, I used to go to a park where there were a lot of people would fly various kinds of either wire-controlled or radio-controlled airplanes. And I remember one guy had a wire-controlled jet model airplane. That thing made an enormous amount of noise. I used to sit next to the wall by the tennis courts while I watched this guy fly this thing. It was a big long cable, a bunch of wires connected to the airplane. He would lean way back as this thing went around. And as it went around, I could feel the sound vibrating all the way through my body as this thing went around and around. It's incredible, the little jet engine that this guy was flying back. This was in the early 1970s. For our next example, let's assume that the acceleration is equal to some constant. Let's say minus g times j. The velocity should be the integral of the acceleration with respect to time. As you can see, I'm assuming here that the acceleration goes down at each point. The j vector going up minus j goes down. The constant g gives you the magnitude of that acceleration. As you can see, if you integrate this, you'll get minus gt times j plus a constant vector of integration. Let's assume that the velocity at time 0 is some value v0. What does that imply? As you can see, if v of 0 is v0, some constant vector, when we plug t equals 0 in to the minus gtj term, we get 0 there plus the constant vector c. Knowing that the constant vector is the initial velocity, that tells us that the velocity is v0 minus gtj. To obtain the position vector, we integrate the velocity. So we'll have to integrate the constant vector v0 minus gtj with respect to time. This, of course, gives us v0t minus 1/2 g t squared j plus a constant vector of integration. If we assume that r of 0 is some initial position vector r0, what does that imply? When we plug in t equals 0, the first two terms will go away and we'll just end up with the constant vector c. So the physical interpretation of the constant of integration in this case is, that is, the initial position. We have then that the position is equal to the initial position plus the initial velocity times time minus 1/2 g t squared j. Further, if we assume v0 is some constant scalar v0 times cosine theta sine theta, and if r0 is some x0 y0 then if we assume that the position vector has x and y coordinates, x and y, we have the x and y coordinates are x0 plus v0 cosine theta times time, comma, y0 plus v0 sine theta times time minus 1/2 g t squared. This gives us a simple model for ballistics. You can see that in this simple ballistics model, x is some initial x plus the initial speed times the cosine of the angle of inclination the object is launched at times t, whereas y is equal to some initial y value plus v0 sine theta times t minus 1/2 g t squared. So we're starting at some initial position x0, y0, launching at some initial velocity through some angle theta, and watching the object progress ballistically, completely ignoring air resistance and other factors. We're assuming here that the acceleration due to gravity is constant, so this is only applicable in near Earth surface motion. If you want to factor in air resistance, which is obviously a very significant factor, you'll have to wait until you take a course in differential equations. There, we'll show you how to model it. For example, suppose that we throw a rock off of the top of Anadarko Tower. If you look it up, Anadarko Tower is 439 feet high. We're going to assume that that's about the height from which the rock is released. Suppose it's released at an angle of 60 degrees from the horizontal and 50 feet per second. Since we're in English units, g, the acceleration due to gravity, will be 32 feet per second squared. We have then x equals x0, which we'll assume is 0, plus v0 times the cosine of the angle theta times t. Y equals y0, which we'll assume is 439 feet, plus 50 times the sine of 60 degrees times t minus 1/2 times 32 times t squared. There are now a number of questions that we can answer. For instance, we know that this thing is going to ballistically go until it hits the pond. There's a pond out here. Let's hope there are no river boats out there at the time. Goes up and hits the pond. We can answer questions like, what's the maximum height? When does it reach the maximum height? When does it hit the ground? How far horizontally does it travel? What is the range? When it hits the ground? How fast is it moving? When it hits the ground, well, I said water. When it hits the pond. We can answer these questions from these equations. When does the rock reach the maximum height? It reaches the maximum height when the vertical velocity is 0. So we'll set 0 equal to dy dt. We expect dy dt to be positive for a while, to go to 0, and then go to negative. It'll reach the maximum height when the vertical component of velocity is equal to 0. The horizontal component of velocity is the constant 50 times the cosine of 60 degrees. Cosine of 60 degrees, by the way, is 1/2. The sine of 60 degrees is √3/2. So calculating the derivative of y with respect to time, we get 0, and then 25√3 times 1 minus 32t. We can see then that t would have to be 25√3 divided by 32 seconds. About how much is that? My calculator tells me that's about 1.35 seconds. How high did it go? To calculate that, we need to plug that time into the y-coordinate and crunch some numbers. My calculator tells me that this is 468.3 feet. When does the rock hit the lake? How fast and what is the range? It hits the lake when the height above the ground is 0. So we need to solve the quadratic equation. 0 equals 439 plus 25√3t minus 16t squared. This is a quadratic. There should be two answers. One will be a positive time, the other one will be a negative time. We don't want the negative, so we'll get rid of the negative on the quadratic formula and take the plus answer. We need to use the quadratic formula. Do you remember it? X equals minus b plus or minus square root b squared minus 4ac all over 2a. Yeah, I know, quadratic formula song to that catchy tune, Pop Goes the Weasel. Sorry for that. My calculator gives me a time of 6.76 seconds before the rock splashes into the pond. How fast is it going? The speed is the norm of the velocity vector, which is the norm of r dot. That's going to be the square root of dx dt squared plus dy dt squared. We need to calculate both of these derivatives and plug them into the formula for the speed and evaluate that at the time t. So x dot is the constant 25. When we take the derivative with respect to t, the derivative of t is 1. Y dot is 25√3 minus 32t. So the speed, which is often denoted by ds dt because s is the arc length along the curve, the speed is the rate at which arc length is being progressed along the curve. That's the square root of x dot squared plus y dot squared, evaluated at t equals 6.76 seconds, gives us my calculator gives me about 175, and the units are feet per second. How much is that in miles per hour? If we divide by 5,280, because there are 5,280 feet in 1 mile, and multiply by 3,600, because there are 3,600 seconds in an hour, we get about 119 miles per hour. That leaves one unanswered question. What is the range? The range should be the x-coordinate evaluated at the time that the rock splashes down into the water. So that's going to be 25 times 6.76 seconds, or about 169 feet. We're next going to talk about arc length and curvature. First, arc length. As we know, the rate of change of arc length with respect to time is the norm of the velocity vector. It stands to reason, then, that we could calculate the arc length by integrating the speed. This gives us something of an arc length parameter. To within a constant, how far you've traveled down the curve at each time. We can also find the total arc length by integrating from some initial parameter t0 to some final parameter tf. This will be some constant. Over here we get the arc length as a function of the parameter t. Let's suppose that we have a position function given by r cosine t, r sine t. As you know, this will be a circle of radius r. And let's find the total arc length as we integrate from t equals 0, and at t equals 0 you're here, to t equals some theta. First, let's calculate the speed. To do that, we need the velocity vector, which is clearly minus r sine t, r cosine t. It follows then that the speed is the square root. Can I use an s for sine and a c for cosine? You can see we'll get the square root of r squared sine squared plus r squared cosine squared. The r squared can be factored out. Sine squared plus cosine squared is equal to 1. The square root of r squared is r. We're assuming the radius is a positive number. So the speed is equal to r. Now, in the integral that results, the integrand is a constant. If you integrate a constant on an interval from a to b, the area will equal the constant times the interval length. We don't need to use the fundamental theorem of calculus to evaluate this integral. All we have to do is take r and multiply it by the interval length. This gives us the well-known formula s equals r theta from trigonometry. The formula s equals r theta is true. It gives you the arc length as you go through some central angle theta in a circle of radius r. S is that arc length. This is only true, of course, if theta is measured in radians. And the derivative formulas for the trigonometric functions that we used in the derivation are also only true if those trig functions are evaluated in angles measured in radians. Let's do a quick example. Find the arc length of the curve r of t equals a cosine of t, a sine of t, and then k t, where t runs from 0 to 3 pi. So 1.5 times around, what is this curve? Where the z-coordinate grows at a constant linear rate? This is a helix. To calculate the length, we first calculate the velocity. The velocity will be minus a sine, a cosine, and then k. The speed will be, you can see we'll have an a squared sine squared plus an a squared cosine squared under the radical. I'll just give you a squared and then k squared. Note that this curve is being traversed at a constant speed. The arc length then will be the integral from 0 to 3 pi of the square root of a squared plus k squared dt. And that then is 3 pi times the square root of a squared plus k squared. In our next example, I want to find the length of the vector valued function t, 4/3 t to the 3 halves, 1/2 t squared, where t runs from 0 to 2. To find the length, the first step is, of course, to find the velocity. That will be 1. When we bring the 3 halves down, the 3's will cancel and a 2 will cancel, leaving us with 2t to the power of 1/2 after we subtract 1 from the exponent. In the last coordinate, the derivative will be t. The speed is the norm of the velocity vector. That will be the square root of 1 plus 4t plus t squared. The arc length then will be the integral from 0 to 2 of the square root of 1 plus 4t plus t squared, being the method. It's not so easy to factor the stuff under the radical. Let's rewrite this as the integral from 0 to 2, the square root of t squared plus 4t. If we complete the square, we want there to be a plus 4. You divide the coefficient of t by 2 and square it. That's what we want. What we have is 1. So to compensate, I'll subtract 3. We now have a difference of squares under a radical. I know, 3 is not a perfect square, but we'll pretend that it's the square of the square root of 3. This is a trig subproblem. Whenever you have a sum or difference of squares under a radical, it's a trig sub. But which kind? There are 3 kinds: sine, tangent, and secant. It depends upon the form of the identity, the Pythagorean identity, that will give you a simplification, the ability to turn this difference of squares into a perfect square that you can get rid of with the radical. Now, we know that cosine squared theta plus sine squared equals 1. This gives you cosine squared theta is 1 minus sine squared theta. So if you have a constant minus variable stuff squared, the substitution is sine. That's not what we have here. We have variable stuff squared minus constant. If you divide everything in sight by cosine squared, you'll have 1 plus tangent squared theta equals secant squared theta. If you have a plus under the radical, that's when you use tangent as your substitution. But here we'll move the 1 over we can see that our substitution must in fact be a secant. Here's how you do this. You take the square root of the variable stuff squared, that gives you t plus 2. You set that equal to the square root of the constant part times the substitution, secant theta in this case. It follows then that dt is the square root of 3 times secant theta tangent theta d theta. Usually, we convert the limits of integration using the first equation for the substitution, though that doesn't give you a very good simplification for t equals 2. So instead, we're going to transform the integral as the integral from dot to dot. That means I'm ignoring the transformation of the limits of integration, and I'll convert back later. Whenever I do that, I don't want to write 0 to 2, because with respect to theta, those new theta limits of integration are not 0 and 2. We'll have the square root of t plus 2 squared will be 3 secant squared theta minus 3 dt is replaced by the square root of 3 secant theta tangent theta d theta. Don't be messing with my notation. This dt is there for a purpose. If you start abusing those differentials, they will abuse you back. I'm going to write our substitution over here for future reference. We have then the integral from dot to dot. The 3 can be factored out here. And the Pythagorean identity, you will recall, was secant squared theta minus 1 equals tangent squared theta. The square root of tangent squared theta will be tangent, so we'll have root 3 from the square root of this 3, tangent theta from the conversion of secant squared minus 1 to tangent squared and then taking the square root. We'll have another root 3. We'll have another tangent, and we'll have a secant theta. The root 3 squared is 3, that will come out of the integral. What do we do to integrate what's left over? Tangent squared theta, secant theta. The trick there is to use the identity that tangent squared is secant squared theta minus 1. This gives us 3 times 2 integrals. The integral from dot to dot of secant cubed theta d theta minus the integral from dot to dot of secant theta d theta. Let's work on each of these integrals independently as little side problems, starting with the integral of secant theta. You might recall that this integral uses a garbage can calculation. The only way to explain what we do next is that some professor must have been walking around in his office one day, pacing, wondering, how do I integrate secant theta, and happened to pass by the garbage can, and there it was, exactly what was required. Before pursuing this any further, I want to recall to your memory integrals of the form f prime over f. As you know, if you set u equal to f of x, du will be f prime of x dx. which converts the integral into 1 over u du, which gives you the log of the absolute value of u plus c, or the log of the absolute value of f of x plus c. Anytime you have an integral of the form f prime over f, you get log absolute value of f of x plus c. What we're going to do is multiply secant theta by secant theta plus tangent theta over secant theta plus tangent theta, because that will give us, if we distribute and then reverse the order of the sum, we'll have secant theta tangent theta plus secant squared theta divided by secant theta plus tangent theta. The derivative of secant is secant tangent, and the derivative of tangent is secant squared. This integrand is now exactly in the form f prime over f, and that means we get the log of the absolute value of secant theta plus tangent theta plus c. You should memorize this. So we know the integral of the second term. How about the integral of the first? It turns out, to integrate this, we have to split off the secant squared theta, keeping in mind that if the integral of secant squared is tangent, you'd rather integrate secant squared and perhaps differentiate secant. That means we should use integration by parts. U is the part you want to differentiate. dv is everything else, including the differential. du, the derivative of secant, is secant theta tangent theta d theta, and v is tangent theta. We have then, in this side computation disconnected from the main computation, that the integral of secant cubed is uv minus integral of v du. I advocate always writing your integration by parts substitution elements in this exact form, with the u, the dv, the du, and the v, and then you multiply always in exactly the same directions each time. uv, secant theta tangent theta, minus the integral of v du, which is secant theta tangent squared theta d theta. Are we any better off than we were 2 minutes ago? Doesn't look like it, but let's see where this goes. Now, tangent theta is secant squared theta minus 1 by the Pythagorean identity. When we distribute, we'll have minus the integral of secant cubed theta, and minus minus makes plus the integral of secant theta, which we know. We just showed that the integral of secant theta is the natural log of the absolute value of secant theta plus tangent theta, and then plus an arbitrary constant. We know that. But here we have what it is that we started with. What do? This is a classic integral where you send this to the other side to join its twin. You end up with 2 of them, and then you divide by 2. Bringing this term over to the left-hand side to join its twin, we have twice the integral of secant cubed theta is secant theta tangent theta plus log absolute value secant theta plus tangent theta plus c. All that's left is to multiply through by a half on each term. A half of an arbitrary constant is still an arbitrary constant. We now have the integral on both of these terms. We have then Continuing with our original computation, 3 times. Now the integral of secant cubed is up here, but we're subtracting an integral of secant, which is a log secant theta tangent theta. We'll have the following: 1/2 secant theta tangent theta. A positive 1/2 minus 1 gives you a negative 1/2 log absolute value secant theta plus tangent theta, but we are evaluating from dot to dot. Now we have to convert back to t. Before that, let's factor out this 1/2. Now, in converting back, we need to use the fact that secant theta is t plus 2 over the square root of 3. Secant is the reciprocal of cosine, so it's hypotenuse over adjacent. It's hypotenuse over adjacent. That makes the remaining side the square root of t plus 2 squared minus 3. Yep, that had better rear its ugly head again, or else you screwed up. We have then 3/2. Secant theta is t plus 2 over root 3. Tangent theta is opposite over adjacent. That's the square root of t plus 2 squared minus 3 all over root 3 minus log absolute value of t plus 2 over root 3 plus the square root of t plus 2 quantity squared minus 3 over root 3 evaluated from 0 to 2. So next we need to plug in 2 and then subtract what we get when we plug in 0. One thing to note, we have a root 3 times root 3. If we distribute the 3, we'll cancel that, but we'll get another 3 here. So we still have the 1/2, plugging in 2. 2 plus 2 is 4. We'll have 4 squared, that's 16, minus 3, that's the square root of 13. Minus 3 times the log, we're going to have 4 over root 3 plus square root of 13 over root 3 minus what you get when you plug in 0 for t. Plugging in 0, we'll have 2. We'll have 2 squared is 4, minus 3 is 1, so that's just 2. Minus 3 times the log of 2 over the square root of 3 plus 1 over the square root of 3. And we could just simplify from there. What does this number represent? That is the length of the curve. Yes, these length problems almost always go straight to hell. And that's the nature of the business. Let me give you another example. Find the arc length parameter for r of t equals, let's say, 4 plus 2t, 5 minus t, where t runs from 0 to, let's say, 2. Here's how you do this. The arc length parameter is going to be the integral from the initial point on the interval sum to some t of the norm of the velocity vector. The velocity vector in this case is 2 minus 1, so that the norm of the velocity vector is the square root of 5. 4 plus 1 is 5. So we are going to have the integral from 0 to t of the square root of 5 dt. The square root of 5 being constant, we simply multiply by the length of the interval. The length of the interval is t minus 0, or just t. So we have the square root of 5 times t. The arc length is root 5 times t. On this particular problem, you might be able to see that this position vector gives you the path of a straight line segment between 0 and 2. Since the curve is parameterized in this way, it's being traversed at a constant speed, and the total distance that you've traveled down is that speed times how much time has elapsed. Before moving on, I want to point something out to you. We can solve for t here and substitute back into the original problem, reparametrizing the curve not with respect to some arbitrary parameter t, but with respect to a parameter that has geometric significance, the arc length. We'll have 2 over root 5s added to 4 and 5 minus s divided by the square root of 5. There are some things that you should note about this reparametrized function. In particular, dr ds is going to be 2 over the square root of 5, negative 1 over the square root of 5. And now, the norm of dr ds will be the square root of 4/5 plus 1/5, and that is 1. When you reparametrized this curve with respect to the arc length s, it is now being traversed at unit speed. Is that always going to be the case? The answer is yes. You can see that if I have the norm of dr ds, that is the norm of dr dt ds by the chain rule. We know that here we have the norm of dr dt, and this scalar can come out. But it can come out as a ds dt, which is always positive because ds dt is the speed, which is the norm of the velocity vector. dr dt is the velocity vector, so in the numerator we have the norm of the velocity vector. In the denominator we have the speed, which is the norm of the velocity vector. So now, when you reparameterize with respect to arc length, you traverse the curve at a unit speed. We can call this a theorem. If s is the arc length parameter, that's evaluated from t0 to t of the norm of v. You can use t here if you wish. You can replace that with a separate variable, absolutely to less confusion. Then the norm of dr ds will be 1 in all cases. When you reparameterize the position vector with respect to arc length, you always traverse the curve at unit speed. Now, I did promise you that we'd get back to some calculus, and I think we've accomplished that goal today. How many of the integration techniques are you going to need to remember in this class? All of them.